Okay, so now I'm gonna do a video. This will be the first of two videos where we talk about the electric field due to a distribution of charge. And first, we're going to think about a ring of charge. So I want to imagine this ring here, and let's say this ring has got some positive charge on it. It's got some charge. Let's call it charge Q. So there's this charge Q distributed uniformly. So actually, let's make sure that we understand that this is a uniformly charged ring. So what does that mean? Well, that means that if this thing is uniformly charged, then there's some charge density, which which we'll represent with the Greek letter lambda. So we could say that there's some charge density where the charge density is going to be equal to the total charge Q over the total circumference, the total length of this thing, circumference, and we could, hold on a second, we just call that, I suppose we call that length L if we wanted to. So this would be, the charge density would be the amount of charge per length L, where L is the entire length of this ring. And this charge density is therefore uniform. And what I'd like to think about is, what would the E field be, the electric field be at a certain point, say a point like right here. So this is some point out in space, and we'd like to know what the field is. And you're going to see we're going to go about this in a certain way that's going to be a pattern that could be used for any uniform distribution of charge. You sort of approach them all the same way, and hopefully that'll be manifest as we go through it. So the first thing I'm going to do is I'm going to chop, the very first step is I'm going to chop this line of charge into, or I'm going to imagine a little element here, some little tiny element ds. I call it ds because we use s for arc length, so I'm imagining one little piece of arc length here. So I've got some little guy ds right in there. And this little guy ds is some distance r, I'll call it little r, away from my point that I'm thinking about. So here's the distance little r away from the point that I'm trying to calculate the E field at. So this is little r. And we need some other, we're going to use some other distances. Let's imagine that our element ds is a radial distance r, big R here, away from the center of the ring. So this is the distance from ds to the center of the ring. And then the distance from the center of the ring to the point where we're measuring the E field, let's call that distance z. So big R here is the radius of the ring, z is the distance from the center of the ring to the point, and then little r is from our point out in space to ds. And so we could first of all recognize that ds is going to exert a field along r, along this line here, and it's going to be some infinitesimal element of E, we'll call that dE, meaning some infinitely tiny amount of electric field due to this infinitely tiny arc length ds. So first of all, we could recognize that, and this is going to be this will be a key thing that we'll note over and over again, that there are two components to dE. There's a component up here that is directed straight out away from the center of the ring, and then there would be a component out to the side this way. And this may or may not be obvious to you, but it turns out because this ring is symmetric, and you'll see that when we're talking about uniformly charged continuous distributions of charge, that symmetry arguments are important. Because this is a symmetric situation, all of these components, these horizontal components, are all going to cancel out. So if you imagine there's going to be some other element ds over here that's going to have an E field dE this way, and that dE is going to have a component to the right which is going to cancel, right? These two are going to be equal and they're going to cancel out. In other words, because this, I'm going to, just to clear up the picture, I'm going to get rid of some of this stuff so we aren't confused. So the point is, because it's symmetric, we can ignore the sort of X element, the horizontal element here. In fact, I'm just going to go ahead and erase this so that we don't have to think about it. So by symmetry, we can ignore that element, and it's only this element here that we're interested in. So let's think about that element. Well, let's first recognize that there's some angle here, theta, which is the same as this angle, theta. So here's theta. Okay, that's theta. And make that a little bit darker. That's our angle theta, so this is theta up here as well. There's theta. And so this element here is going to be dE times the cosine of that angle theta. Okay, so ultimately it's going to be this component or this piece of E that's going to be relevant. The sine, the component dE sine theta, that would have been this horizontal component, we're going to ignore. All right, so let's get started here. First of all, before we get started, one other little bit of groundwork. I mentioned before charge density, lambda is Q over the whole length L. Well, we could make the same, by the same logic, we could make the argument that lambda is dQ over ds. So if we imagine this is the charge density, well, if I have some tiny element ds, it's going to have a charge on it dQ on this ds. So just to remember that argument's going to come in handy later. All right, so let's get to seeing how we could calculate the electric field. First of all, I'm going to go ahead and say, I'm going to start off by saying dE, so I'm going to focus right now on this guy. I'm going to say that dE, we could calculate that by using our equation for the electric field. So 1 over 4 pi epsilon 0 times dQ over r squared, little r squared. I'm just going to try to make this a little bit smaller. dQ over r squared. So what is this? This is just our equation for the electric field, right? This is 1 over 4 pi epsilon 0 times q over the distance r squared. I'm calling it dq because I'm interested in dE. So this little element, this little amount of charge dq on element ds contributes dE. Hopefully that makes sense. Now, since I have made this point over here, I can rearrange this and say that dQ equals lambda ds. I just rearranged this to say dQ equals lambda ds, and that allows me to say that dE is 1 over 4 pi epsilon 0 times lambda times ds over r squared. So I just substituted lambda ds in for dq right there. One more substitution is I'm curious to know what r is in terms of theta, and you're going to see why I'm doing this later. I'd like to know, I'd like to come up with another way of expressing this distance r in terms of z and big R. So what we could say here is if I note that this is dE cosine theta, I can go ahead, so I've got a right angle right here, so I can say that R equals the square root of z squared plus big R squared. This is by the Pythagorean theorem here. So little r equals the square root of z squared plus big R squared, and so that allows me to rewrite this. Continue down here. 1 over 4 pi epsilon 0 times lambda ds over r squared. Well, r is this square root of z squared plus r squared, so this is just z squared plus r squared. And I'm doing this because I'd like to have E as a function of the radius of the ring and this distance z, not of little r. Little r isn't really intrinsic to the problem, whereas z, the distance from the ring, and big R, the radius of the ring, are intrinsic. Okay, so now where can I go? Well, again, I'm only interested in dE cosine theta. So let's go ahead and rather than talk about dE, let's talk about dE cosine theta. So I'll continue down here. dE cosine theta. What does that equal? Well, that's just this component here. And let's note that theta, cosine theta, right? Theta, cosine of theta, that's adjacent over the hypotenuse. So what I can say here is that the cosine of theta equals z over r. So maybe I'll I'm running out of space here, but I'll put that up here. I'll say cosine theta. The cosine of this angle is z, the adjacent over the hypotenuse r. Z over r. But remember, we like to call r the square root of z squared plus big R squared. So I'm going to write cosine theta equals z over square root of z. Sorry, I'm going to run out of room there, aren't I? I'm going to say cosine theta equals z divided by the square root of z squared plus r squared. And now I can go ahead and say that this whole thing, therefore, is going to be equal to z, sorry, 1 over, let's start off with 1 over 4 pi epsilon 0 times, what is this? We're not going to have, we don't have lambda ds here. We have now z times lambda divided by, well, now what's on the bottom? I've got z squared plus r squared times the square root of z squared plus r squared. So that's z squared plus r squared to the power 3 over 2. So what have I done here? Just so we're clear, this is getting a little bit complicated, I know, but just so we're clear, what I've done here is I've multiplied this whole thing by z over the square root of z squared plus r squared. That's what I've done. So that's where this z is coming from, and that's where this power 3 over 2 is coming from through that multiplication. And by the way, hopefully you caught this. I forgot my ds over here, times ds. Okay. So a lot of substitutions, and it looks like it's gotten more complicated, but this will be ultimately fruitful, I promise. So let's continue. So now what can I say? Well, I can say that the electric field overall, E, is the integral, and the whole point here was to get an integral, the integral of dE cosine theta. Okay, in other words, dE cosine theta, this is one kind of contribution, one infinitesimally small contribution of electric field, and I want the integral of an infinite number of these little dE cosine thetas, right? So each of these elements, there's an infinite number of elements ds, each of which contributes some dE, and I'd like to integrate all of those dEs. And the integral of dE cosine theta now, I know what that is, right? That's going to be the integral of this whole thing. And if I look at this whole thing, everything in here is a constant except for the ds, right? This whole thing, just so we're clear, this whole thing here is just a constant, okay? 1 over 4 pi epsilon 0, those are all constants. The lambda, this is continuous charge distribution, so the lambda is a constant. Z is a constant. We defined this as some distance away from the center of the ring. R, the radius of the ring, is a constant. In other words, this whole thing is just going to be 1 over 4 pi epsilon 0 times lambda z divided by z squared plus r squared to the power 3 halves times the integral of ds. And this is going to be from 0, what is it going to be? Well, it's a full ring, so it's 0 to 2 pi r. So from 0 all the way around to 2 pi r. Well, what is that going to equal? Pretty, hopefully, fairly straightforward to calculate from here. Take the integral ds from 0 to 2 pi r. So what are we going to get in here? We're just going to get a 2 pi r. So we get 1 over 4 pi epsilon 0 times, what do we have up here now? This is just 2 pi r, okay, times lambda. So lambda times z times 2 pi r divided by, down here, z squared plus r squared all to the power 3 halves. So that's now an expression for this field. We can clear this up a little bit because you might have noted that if we have this whole thing right here, lambda, the charge density, times the entire ring of charge, what is that going to be? If I have the charge per unit length times the entire length of the ring, what is that? Well, this whole thing is just big Q. That's the charge on the whole ring. So I can simplify this a little bit, and I can say that now this is going to be 1 over 4 pi epsilon 0 times ZQ. Q is just the overall charge divided by Z squared plus R squared, all to the power 3 halves. Okay, and that is our final result that we're looking for in this long, potentially tedious derivation, and that is our final point. Now, the actual result is less important here than the general reasoning that we went through, and the general reasoning might be worth noting what we did. So if you have a continuous charge, so continuous charge distribution, the first thing is construct little elements, integrate those little elements, and then almost always the way this is going to work is there's going to be some very important symmetry argument that you make, because without this technique, without some sort of symmetry, is frequently not very helpful. So the symmetry argument, in this case, you could see the symmetry argument we started off was to ignore, remember we ignored this horizontal component. So hopefully the strategy made sense to you and ultimately led to this result. I guess what maybe while we're discussing this, it might be worth making some point. What would happen to this result that we got here, right here? What would happen here if we had a situation where you had Z being much bigger than R? In other words, what if you had this charged ring here, and what if you were a huge distance way up here, maybe a huge distance away from that charged ring? What would this equation look like? There would be a way to simplify this. If Z were way, way, way bigger than R, then the fact is this term down here, this thing, your Z squared plus R squared, would essentially be equal to Z squared, right? So this whole thing would just be Z squared. And then you could see this would be quite a bit simpler. You'd end up with the situation where you'd have the E field would be 1 over 4 pi epsilon 0 times Q, our Q up here, over Z squared. Because this whole thing would be Z squared to the power 3 halves. You have a Z up here, which would cancel out, and you end up with Z squared. So that's a nice, interesting, handy result. What does that mean? Well, that means that if you're very far away from the charged ring, and this I think maybe intuitively would make sense, what does the charged ring look like if you're very far away? Well, it looks like a point charge. It looks like a single charged point way off in the distance. A teeny tiny ring very far away would behave very much like a point charge, which is what this is the equation for, right? This is the electric field due to a point charge. So interesting result. That's all for now. Next video, we're going to look at a slightly trickier charge configuration.